So if we focus on just this, by uniqueness, remember we said the southwest glue tuples have to be unique. Well, if there's only one green tile, it would basically have glues that say green blue. And if that green tile appeared here too, then this diagonal right after it would also have to be blue. It couldn't be teal. So we're going to need at least 2 tiles that are colored green. I'm just trying to give you a little bit of an intuition for some of the concepts that the model is playing with. Okay, so we have just 2 more patterns here. We're going to slowly build up complexity. This pattern on the left has a lot of structure, right? It's just this simple red line, and that it's symmetrical around axis here and here. But a minimal tile set is really not obvious. I can't actually compute one. And then this pattern on the right is our original random pattern that I had used to describe color patterns. And it's likely that we're going to need a unique tile to put at every individual index. Okay, so I want to show you some of the power that's built into this model. So this is the Sierpinski fractal. And let's assume that it's a 2-color pattern. How many tiles would we need to generate something like this? Well, the answer is just 4. So we have the tile set T here. There are 2 white tiles. There are 2 black tiles. The glues are just red or blue. And with a seed of all 4s on the bottom and all 3s up the left side, we can build an arbitrarily large Sierpinski triangle. And one thing that I really want to highlight is that this is an example of really complex behavior emerging from really simple local rules. Okay, so existing work. The past problem was introduced by Mon Lombardi. The tile assembly model that I've been talking about is by Winfrey. Seisler and Hoppe show paths as NP-hard in the general case. So what I mean by the general case is a color pattern has as many colors as you want to say. But we want to talk about small tile sets, so it makes sense that we would also want to talk about small numbers of colors. And my co-author Seki broke the constant barrier by proving that 60 paths is hard. And what we do in this paper is we cut it in half to say that 29 paths is NP hard. And so why is this result interesting? Well, first of all, I want to come back to the motivation, which is that we can actually do these computations, these self-assemblies in the lab. So not only is this a first step towards determining small tile sets for determining certain circuits, but also as we build up the proof, there's an efficient tile set to simulate subtraction that comes out of this. So we're learning something about computation in this model. And the result requires over 100 gadgets for the reduction. And then, proving that we belong in this session, we also get an inapproximability result of 47 over 46. This is for the size variant of paths, which says, just tell me the size of a minimal tile set. Don't actually tell me the size. Okay, so I only have a couple minutes left, and I'm going to run through the rest of this pretty fast. I don't want to go through the reduction. It's technical and not interesting in the end. What I'd rather do is try to give you an intuition for what something looks like when we do computation in this model, which is subtraction. Just simple subtraction. So the reduction is from subset sum, and we can imagine subtraction appearing in this. I think you all know that. I think you all know the definition, and you've had a couple seconds now to read it, so I'm going to continue on. What we want to do is encode 2 numbers. Let's say we want to subtract 11 from 75. We want to encode these numbers as colors. So we'll just make up 2 colors. We'll have this 0 black and this 1 white color. And now we're going to put them into our L-shaped seed. So up the left-hand side, with most significant bit at the top, we're going to write 75. And across the bottom, with most significant bit at the right, we're going to write 11. Now, if we want to do subtraction, it would make sense to line up the bits, and we can imagine that the bitwise subtraction would be taking place at these indexes within our color pattern. So we want, like, we should want something special to be happening in these indexes of the color pattern. And that will actually be, right, this will be a color that represents implementing a half subtractor. Okay, so I've showed you this before. This light blue color is a half subtractor. To complete the carry operation, we're going to put this everywhere above these red X's. This will guarantee that the inputs to the red X's coming from the left will be accurate. So if we subtract one from 0 here, which we don't, but if we did, then that would correctly flip the bit so that the input coming into the left side of this red X is accurate. And then below the red X's, all we want to do is preserve information. We want this bit to get to this red X correctly, and we want the output here to make it all the way across. Now we're going to use these patterns as gadgets to basically train the reduction to know how to do subtraction, to know what these tiles have to look like if we're going to be able to do subtraction with small tile sets. So we would put the correct output at the end. So I just want to show you what the final circuit actually looks like. This is a representation of subset sum, where we would actually start with the target number on the left, and then sequentially, we would possibly, or possibly not, subtract each element one by one as we move to the right. And then it's possible for all of the gadgets to appear somewhere out here. So additional work and open questions. Saki and I have a new construction that for 11 paths. And also he is working with some people at Caltech and using a brute force computer search to do 4 paths and 2 paths. But we still want an intuitive proof of 2 paths, and we want to be able to find approximately small optimal tiles.